In our last episode, we built the prototype circuit for the 555 timer. It was designed to work from 500 hertz to 3 kilohertz. And if you remember, when we hooked up the oscilloscope to test it, we saw a spike on the rise side of the waveform. We talked about this being switching noise. In this episode, we're going to investigate that noise and determine what's causing it and try to fix it. Okay, we're set up in the lab. We have our oscilloscope set up. We have our breadboard with our circuit ready. We have our scope hooked up. We have power disconnected right now, but I have my meter connected because I want to verify my power supply voltage. I don't want over voltage or under voltage. I want to be as close to 5 volts as possible. So I'll switch on the power supply and you'll see we're at 5.086, very close. This should be anywhere from 4.8 to 5.2. It doesn't have to be that accurate, but pretty close to 5 volts for this test. So now, given that, we can connect up our power. So we'll connect up the power here. And you'll see on the scope, we have a signal. So I'm going to increase the time base so it's easier to see that. And you'll see we have that spike on those square waves. So we were looking into the switching problem and why we have that situation occurring. We do know that because we have these long leads, it adds parasitic resistance and capacitance, which complicates the nature of this 555, which has transistors inside that are switching on and off, on and off. Anytime you're switching, you have sudden draw of current, and any micro resistance that occurs causes voltage to shift and can induce various characteristics in the waveform. In looking at this, I realized, however, that I missed a major component. We need a capacitor from pin 8, the 5 volt pin, to pin 1 or ground, as close to the chip as possible. Now why? We need that for that very reason, because as current is drawn in these long leads, you have parasitic capacitance and you have deviation in the potential between 8 and 1. So what we often do is put a capacitor between there to kind of stabilize the micro shifts in the signal across the power supply. It's called a decoupling capacitor. It kind of decouples high frequency and those micro shifts of those noise characteristics. Oftentimes they'll put those decoupling capacitors under the chip or very close to the pins. Now here, we're not going to be able to put it as very close, but we should be able to add a decoupling capacitor and see the waveform change or improve. So let's do that. This is a little 0.01 microfarad tantalum, and usually you use like a 0.01 or 0.1 microfarad for decoupling. It's a good range for the range of frequencies we're interested in decoupling off of the power supply line. So I have a little spot here. I can try to slip it in, but it's going to be kind of tricky. So I'm going to turn the power off to make sure I don't short anything, and we end up having a smoke test. So let's see if I can get this component in place. Should be fairly straightforward to do it. I'm going to go from pin 8 to my ground lead here that I've temporarily put in place. Of course, it's a long lead. You would normally, you don't really want that. On a circuit board, the ground trace would be very close, and it would be like very close to the chip or across 8 and 1. But just for this purpose, this should be good enough to demonstrate what I'm talking about. So let's power it up and see what happens. Cross your fingers. Oh, look at that. Isn't that amazing? Look at that spike. It's reduced dramatically. You still have some spiking going on a little bit, but a much better shaped waveform. Now let me spread it out a little more for you. There. Really nice looking waveform. So what we learned from this was that you can forget components that help decouple noise and high frequencies off of the power lines and help compensate for that switching, because the switching introduces that the sudden transition in engineering theory is really represents all frequencies and high frequency noise. We're going to look and investigate how to clean up the rest of these little spikes, and we're going to look at using a low pass filter for that purpose in the next episode. We're also going to look at a software package called Ltspice. Ltspice is provided free to the engineering community for doing signal analytics, signal characterization of analog circuits. So we're going to actually be able to build a low-pass circuit and even this 555 timer circuit and actually see it run and see the output just as you would see on the scope, except you never used an active real component. It's all going to be in software. Very valuable tool. Engineers use it all the time in the early stages of evaluating circuit design before their first prototype phases. So next time, join us for episode 4, where we design a low-pass filter in Ltspice, test it, and then implement it on our breadboard.